Okay, next exercise 16. Here we are given two groups G and H that are isomorphic to each other. We have to prove that their automorphism groups are also isomorphic to each other. So let's see the solution. Because it's given that G and H are isomorphic, so there is an isomorphism. Let's consider one such. Let phi from G to H be an isomorphism. Now using this phi, we are going to define a map from the automorphism group of G into the automorphism group of H. And then in steps, we are going to show that that map is an isomorphism, proving that these two are isomorphic to each other. We define a map. Let's call this map P. You can call it whatever you want. The name does not matter. By this rule, P of psi is equal to phi psi phi inverse. Okay, so now we have to first of all make sure that this T is a well-defined map, because after that only we can see what else it is. So the first thing we have to see is that this composition is in fact an element in the automorphism group of H. And in verifying that, you have to first of all make sure that this is actually a function from H to H, because otherwise how can it belong to the automorphism group of H? So we already know that phi maps G into H. So that means phi inverse takes us from H to G. One more thing. How is it that phi inverse exists? That is because phi is an isomorphism. So phi is a bijective function. So its inverse naturally exists. So that inverse takes us from H to G. And then this psi is our input. So it is coming from the automorphism group of G. That means psi is an automorphism of G. So it maps G into itself, and then phi, after applying these two things, we apply phi, so that again takes us back to H. So yes, our composition is actually a map from H to itself. So that's the first thing we are going to note. Note that phi psi phi inverse maps H into itself. And then there is one more thing that we can immediately say from properties of functions and their compositions. Because we know that phi is an isomorphism, so that means it's a bijection, it's one-to-one and onto. And psi being an automorphism of G is also after all an isomorphism, so it's a bijection as well. As a result, phi inverse itself is also a bijection. First of all, it exists because phi is a bijection, and then we already know from properties of inverses that it is a bijection itself. So that means here we are looking at a composition of three bijections, and from properties of compositions we know that this composition itself is a bijection. So that is our next thing. Also, since we are of course, let's mention that also, that phi inverse is a bijection. If you want, you may not mention it because it's a consequence of the fact that phi is a bijection. Also, since phi, psi and phi inverse are bijections, so is phi psi phi inverse. Okay, so it's also a bijection, but still we are not able to say that this function belongs to the automorphism group of H, because that one extra condition also has to be verified, that is, it respects the binary operation in H. So for that, let H1 and H2 be two elements in H. Then H1 is equal to phi of G1 and H2 is equal to phi of G2 for some G1 and G2 belonging to G. What is the guarantee that G1 and G2 exist? That's because phi is onto and H1 and H2 are coming from H. That's why such inverse images exist of H1 and H2. But then from these equations, what do we get? G1 is equal to phi inverse of H1 and G2 is phi inverse of H2 by definition of inverse function. Now let us apply this composition function on the product H1, H2 in order to see whether it respects the binary operation. So that means what we are saying is this. H1, H2. Okay. That is equal to, so let's write what H1 and H2 are, what we have found here. Phi psi phi inverse. H1 is phi of G1 and H2 is phi of G2. Now since phi is an isomorphism, so phi itself respects the binary operation in G, of course, between G and H. So this is equal to phi of G1, G2. Now because we are dealing with composition, phi and phi inverse will give us the identity map. That means we are going to get this next. More loosely speaking, they cancel out and we are left with this. But then by the definition of composition, this is what? G1, G2. Because psi is an isomorphism, psi is an automorphism but an isomorphism also, we have this. But phi also is an isomorphism. So that's why the phi also will distribute itself over this product, and we will have this psi of G2. Okay. Now in place of G1, what we can do is we can bring back phi inverse and phi. And you will understand if I write things directly like this: phi psi phi inverse of phi of G1 times, I don't have space here, phi psi phi inverse of phi of G2. And that becomes what? If you recall what phi of G1 is, phi of G1 is H1. You then get phi psi phi inverse of H1 times, well, times means you need not write anything, of course, phi psi phi inverse of phi of G2 is H2. So there we have it. Phi psi phi inverse actually respects the binary operation in H, because it's a function from H to H. So now we can say, hence this is an isomorphism, i.e. isomorphism from H to H, so it's an automorphism of H. Yeah, now we can finally conclude this. So the function that we defined, which maps psi onto this thing, this object, actually maps an automorphism of G onto an automorphism of H. And from the definition, it's clear that for a given automorphism psi of G, this is a unique automorphism of H. So we can now just simply write this as conclusion. So T is well defined. Okay, so far we have only shown that T is a well defined map, but now we have to show those further things about T. That T itself is also a bijection, and T also satisfies that condition, that is, T also respects the binary operation between these two automorphism groups. Next we are going to show that T is injective, it's one-to-one. For that, let psi1 and psi2 be two automorphisms of G such that T of psi1 is equal to T of psi2. Our aim is to show that psi1 is equal to psi2. Then so by the definition of T, phi psi 1 phi inverse is equal to phi psi 2 phi inverse, which implies because we are after all dealing with bijective functions, the next thing we can have which follows from this is this phi inverse phi psi 1 phi inverse phi is equal to phi inverse phi psi 2 phi inverse phi. Because if these two maps are equal, then these two compositions also will be equal. But now, using the fact that composition of mappings is associative and cancelling out these things, you can clearly see that ultimately we have this. Hence, T is 1 to 1. Okay. The next aim is to show that T is onto. For that, let F be any automorphism of H. We want an inverse image to which if we apply capital T, then we are going to get F. Consider the map phi inverse F phi from G into G. Is it really a map from G into G? Let us first see that. Phi takes us from G to H because phi is the big thing in the beginning. So phi takes us from G to H, and then F takes us from H to what? H to itself. Why? Because we have chosen F to be an automorphism of H. So after all, it's a function from H to itself. And then phi inverse takes us back to G. So yes, this composition is a map from G to G. Now our aim is to show that this is the first thing we are now going to show is that this composition actually is an automorphism of G. Okay, so that is the first thing. And then of course we will show that its T image is F, which is rather easy, almost obvious. Since phi F, phi inverse are all bijections, so is this composition. Okay, so this part is over. Now the next thing to show is that this map respects the binary operation. Let G, okay, so we used G1 and G2 back there, right? Let us take something else. Let's just take X and Y. And apply this map on the product XY, and let's see what happens. Well, can we just simply go for the calculation, or should we do? Let's just write the thing, and if we need something, we will then have to change things accordingly. Let's just straight away, without thinking too much about it, let's try to calculate this. Let's see what we can do with this. By the definition of composition, it's just this. But phi is an isomorphism, we already know, so it respects the binary operation. So that means this will be equal to phi inverse f of phi of x times phi of y. But then on that we are going to apply f next. And just like phi, f is also an isomorphism. In fact, it's actually an automorphism. So it also respects our thing. Okay. So after this, what shall we do? Well, we already know one thing. Okay, we already know that either we know or it can be proved very easily that phi inverse, just like phi, itself also respects the binary operation. What I am saying is this. It's a fact which is already available in the text or not. I am not entirely sure. I have not gone through the part fully. I am just simply solving the exercises now. So phi is a map from G to H, right? From the beginning itself, this has been the thing. And phi inverse is a map from H to G. Now phi respects the binary operation. Does phi inverse also respect the binary operation? You see, we already know from the theory of functions or from properties of functions that because phi is bijective, phi inverse as a function is also bijective. But phi respects this rule, phi of G1, phi of G2, where G1 and G2 are coming from G. Is this the same thing for phi inverse? It is. H1, H2 is phi inverse of H1 times phi inverse of H2. It does not take too much of effort to establish this fact from the fact that phi satisfies this. And here, of course, H1 and H2 are coming from H. Now, I am not sure whether this has already been done in the text. If not, then I leave it to you. So that's the thing we are going to use here in the next step. So you can understand what we are going to write next. Phi inverse of f of phi of x times phi inverse of f of phi of y. That's the thing. If you somehow are unable to establish this fact, then and at the same time, if this is not available in the text, please write in the comment section below. Okay, we can do there. So this will be phi inverse of f of phi of x times phi inverse of f of phi of y. But then that is just simply this composition evaluated at x times that same composition evaluated at y. So that's it. It's a bijection, and as well as it satisfies this property. Hence, phi inverse f phi is in fact an automorphism of G. Now we can apply capital T on this, because now it has become a point in the domain of capital T. Also, this by the definition of capital T is going to be this. So that's it. For a given automorphism of H, small f, we have found an inverse image under T. So that just proves that capital T is onto. So we have proved that capital T is one-to-one and onto. Now capital T also has to satisfy this condition of respecting the binary operation, because then only we can say that capital T is an isomorphism. For that, let us again choose two elements in the domain of capital T, which is the automorphism group of G, and we apply T on their product in this group. So by definition, this is what phi uv phi inverse. But you can almost guess what we should write next, given that you already know something about inner automorphisms. The middle phi inverse and phi, they cancel out, and we are left with just that. So that means this is nothing but T of u, and that one is T of v. So now we can claim that T is an isomorphism. This shows that T is an isomorphism, i.e. the automorphism group of G is isomorphic to the automorphism group of H. Okay, so that's how they are isomorphic. Actually, if you do not treat isomorphic groups as something different at all, then this is almost trivial, but still it demands a rigorous demonstration, which is the solution. Usually in group theory, when you encounter isomorphic groups, actual concrete isomorphic groups, well, you may just simply say that they will be equal to each other, identical. That may not be the case. Sometimes isomorphic groups appear differently. Differently means one group will look like something, another group will look like something else entirely. But you know what the isomorphism is in between them. So you should also be able to then see how exactly the automorphism group of, say this is G, is isomorphic to the automorphism group of H. Okay, so which is why we have this thing, this device, this map T. Using that, you can see which elements in the automorphism group of G correspond to which elements in the automorphism group of H. Okay. So let's now see the next one. 617. Suppose phi belongs to the automorphism group of Zn or Zn, the group of additive group of integers modulo n, and A is relatively prime to n. Well, that means A is an integer that is relatively prime to n. Okay, if I think I need a little ink. It is really dry over here with no rain for many days. So things are drying up extremely quickly. So what is it if phi of A is equal to B? Determine a formula for phi of x. Well, phi of x means where x is any element of Zn. From the equation phi of A equal to B, we get A times phi of 1 equal to B, which of course you understand why it is happening. That's because phi is an automorphism of Zn, and in Zn, A means what? A means 1 plus 1 plus etc. plus 1 A times, if A is positive, and you also of course know the other meanings when A is 0 and when A is negative. So A actually in this group, A means this, the eighth power of 1. That's what A means. We do not normally write A times 1 because that's how we normally write such things, such an integral power of group element in an additive group, in an abelian group. That's how we write things. Here, however, the author is just simply writing A. So Now, if on this you apply an automorphism, then you know that this just simply becomes the eighth power of phi of 1 from properties of automorphisms. And that eighth power of phi of 1, if you translate things back to this group, because we are dealing with an abelian group, is just 8 times phi of 1. That means again, if A is positive, then the meaning of this is phi of 1 plus phi of 1 plus phi of 1 and so on, 8 times. 8 copies of phi of 1 has been added together, and that is B. But from this equation now, this one, we can say something else also. Since A and N are relatively prime, that means their greatest common divisor is 1. A belongs to this group U of N, consisting of all the positive integers less than n and relatively prime to n. We have this, and so A inverse exists in U of n, and U of n is, as a set, it's just a subset of our system. So that means this A inverse actually exists here also. It well, you already probably know about rings. This is a ring as well now. So this A is an invertible element in this ring. It's a unit element, that is an element whose inverse also exists in the ring. And since this equation is after all an equation in this ring, so we can now use the inverse to next write from this equation this. A inverse B. Keep in mind, we are not using any field properties or anything, if you know what that means, because Zn is not a field unless n is a prime number, and we don't know if it is a prime number. It may not be a prime number, but still, in spite of that, just being a ring from this equation, you can have this. For that, what is it that you should do? You multiply on both sides by A inverse and simply use the ring axioms. That's it. Distributive law, associativity of multiplication, those things, okay. No need to assume such thing that this is a field. We don't need that, and it may not be a field. But now, for any x in z of n or z of n, phi of x, just like phi of A is A times phi of 1, phi of x is also x times phi of 1. But phi of 1 is A inverse B. So that is a formula for phi of x. So if it turns out that A is relatively prime to n, A may be any such element in Zn, then the phi, that is your automorphism, can be given by such an explicit formula, where you know what A inverse is and you know what B is. B is actually nothing but phi of A. So if you want, you can write phi of A here, then everything will be in terms of A. and x of course will be there because x is your input. So that is the formula. And let me just end the video here itself because the heat is unbearable. And I suffer a lot because of my skin allergy. And for that only I have to be like this. But anyway, tomorrow we have another upload. So tomorrow we are going to see more on uncountable sets because we have started that in analysis. So let's see what more comes after what we have done. In the previous video. So see you tomorrow with more on uncountable sets. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.